And the last one is 2153. Okay. So now when you look at this number, you're like, B is what? B and N is describing this region now. Okay, B and N, we are now describing this region now. Okay, we're in this region now. Okay, so we know A, right? Now we are going to B and N now. Now we are looking at B and N. Okay, so B and N, then we start ranking again. Okay, so as usual, 4, 6. This is number 1. Fine. This is number 1. No problem, because we know that it was difficult, right? But it's not necessarily twice more difficult. It's much more what? Difficult than our what? Benchmark, right? Maybe you charge $4. Maybe it's not enough money, man, right? And then now this become what? Number 2. Okay. Now this become number 3, and now AISI 1045 becomes the what? Becomes the easiest. That's where the problem is, right? If you look at the A value is just the initial flow stress. It is just this point out here. This is where A value is, right? You cannot use that A value to make decision, which is equivalent to what? The hardness. Up to today, as we speak now, I have so many times whenever I'm doing my consulting, I have industry call me, Eugene, we have this material, we have how hard. Is it easy or going to be difficult to deform? I say, no good. No good. I can't tell you much. Okay, I need more information. I need the information where how this curve is increasing. Okay, and then the next one is our N. All right, so N over here is unitless. There's no unit for N. So this is 0.234. And then you have 0.253. Okay. And then 0.196. And then you have 0.66. Okay, you have 0.66. And then over here, we start looking at N, and then our ranking system gets skewed up again, right? So now this is number 1. Right, 0.66 is number 1. And then this is our number 2. And then this is our number 3. And then this is our number 4. Okay. And then I'm going to introduce you another column, which is our microstructure. So we are going to look at our microstructure. All right, we are going to look at our microstructure at the edge. So the microstructure for AISI 1045, you have ferrite plus pearlite. Can anyone tell me which is the softer one? Anyone?
Pearlite.
Ferrite. Okay, it's like 50-50, you cheeky sort. Ferrite is softer, right? Right? It's easier to deform. Pearlite is harder to deform. Why is pearlite harder to deform?
It has a higher carbon content.
It's a higher carbon. Ferrite and pearlite, they do come together. Carbon content is AISI 1045. But why is pearlite harder to deform?
Because it has more steel.
It has more steel. Where are you? It's not it has more steel, okay? Because pearlite is a what? It's a compound. It has combination of ferrite plus cementite, and cementite are ceramic plates. Don't worry about all this, okay? I will teach you all this in the next week, okay? So don't worry about all this first, okay? Then Uzbor is what? Martensite. And wherever you see this microstructure, martensite, you're in trouble. Okay, you're in trouble. It's going to be difficult. Okay, it's going to be difficult. Then we have martensite. Right, so for dual phase steel, we have martensite plus ferrite. Right, so from here automatically you can see, hey, you can observe that why, right, dual phase steel you only have 120, Uzbor is 1040, because you have what? ferrite. And ferrite are meant to be soft, right? And but they're tough. Okay, ferrite are very, very tough. And the last one, right? And last one is our so-called trip steel. Okay, later on I'll explain to you why trip 800 is not because it's going on holiday. It's it's going to be going 800. Okay, so you have martensite, right? You have martensite. Then you plus bainite plus ferrite. And then plus I need one more. This material is like when you are not sure what you're doing, you have a bit of everything. Yes or no? And then we have, that's just a joke. Okay, they know what they're doing. And then you have something like retain austenite. Okay.
Professor,
Yes.
if there's anything written under retained austenite, it's off the screen and we can't see it.
Okay, I know that. Thank you. I can see that. Okay. So now if we add everything up, okay, if we add everything up, so 2 plus 4 is 6. So this one is 9. Right? Then you have 1 plus 1 plus 2. So this is 4. Right? So I'm just adding everything up, right? So 4 plus 4, 8. This is 11. Right? And then 3, 5, 6. This is 6. So now, once you start looking at these new numbers that we have, right? So probably what you'll do now is you look at your charge differently now. Yes or no? Right now, the most difficult is going to be what? Uzbor is still the same. So Uzbor, probably you can also charge $4 or more. Yes. Then the next most expensive is going to be your what? It's going to be your trip. Right, so if I'm going to put the new value now, the new value, so this one I probably will charge $6 now. Okay, trip steel probably now I'll charge $5. Okay, then the next one is 1045 and steel. Both are not so far away, so both of them I'll charge $2. Now this is looking at both your what? Both your elastic behavior and also including your what? Your plastic behavior. Right? So if you look at the costing now, you realize that like if you're going to treat dual phase steel before, right? You're going to look at dual phase steel. If you're going to charge 50 cents, you're a bit of a trouble. Why is that? Why will you'll be a bit of the trouble? Right? Because it is not that easy to deform. If you look at A value, it's really, really easy. But if you look at B and N, it's not so straightforward. Okay? So now, what I'm going to do is, I'm going to take out two materials now. Okay? I'm going to take out two materials. And then we're going to do some analysis. Okay? So what I'm trying to do over here is by looking at the mechanical properties, can we somehow come up with a trend to cause them to as a factor to cause the to price the manufacturing cost? Okay, how much is it to deform the material? Okay, right. So we are going to focus on two materials now. Okay, we're going to focus on two materials now. Anyone, any question so far? Anyone? No? Okay, so we're going to look at two materials now. Okay, so we are going to look at example. We are going to look at AISI on AISI 1045. Okay, and dual phase steel 600. Okay, so I'm going to sketch the behavior. Okay, as I said, this is just a sketch. Okay, the behavior of dual phase steel and AISI 1045. Okay, so we're going to currently just maybe look at just room temperature. Later on, then we start adding on. We look at higher temperature. Then we also start looking at higher strain rate. Okay, so now we will sketch out. Okay, so this is maybe a bit more. This is 500, so 0. So this is your stress in MPa. This is your strain. So this is 500. Right, you can see 500, 1,000, then 1,500. Then you have 2,000. You have 2,500. Okay. And then we're going to sketch. So the first sketch I'm going to do 1045. So 553.1. So 553, we know the 553 is over here. Right, so I just going to do, so B and N is 600.8 and 0.234. So we will do this. Okay, so this is AISI 1045. Okay, and then we will come to dual phase steel 120. Okay, so this is 553.1, and then we are going to look at dual phase steel. Okay, so we are going to look at a point down here. So over here, this is my 120, right? And because of the B and N, especially the B value is twice, so at one stage, it will cross over. Okay, and when everything like typical engineer, if there's a crossover, it is exciting. Okay, if there's no crossover, it's going to be boring. So this will be for our dual phase steel 600. Okay. So what I want to highlight is this. At a certain point, so at this point, right? At this point, somewhere down here, this is not. I don't know where is it. Okay, somewhere down here. Right, somewhere down here. This line that I've drawn, this location that's drawn, I'm going to call epsilon OPT, which stands for strain optimum. Right, I call it strain optimum. So what this strain optimum, why this point is of interest, is because at the strain optimum, epsilon optimum, okay, the energy required, yeah, I can write here, energy required to deform both materials are the same. Okay, right, the energy required to deform both materials. So energy is area under the stress strain curve. Okay, so if we look at AISI 1045, so AISI 1045, the amount of energy required to induce deformation is this amount. Okay, so this is our AISI 1045. And then if you look at our dual phase steel, right? So dual phase steel will be at this is the energy is this amount. Okay, so the shaded, right? This is for, sorry for it to be so messy, right? So that is for dual phase steel. And at the epsilon optimum, the area under the curve will be the what? Will be the same. Okay, so why is it? Can anyone tell me why is it important to find this optimum? Anyone, please. Why is it
To see which
important?
one's cheaper.
Huh?
To see which one's cheaper.
How do you mean? You are right. Okay. Okay. What do you mean? Which one